Okay. I kept messing up on this, writing this on the board, so I just wrote it once. So I'll talk through it. Here's a proof that this map is a covering space. What is this map? Remember the topological space of configurations of k points in anything, such as Rn? An element of it is just a list of elements of Rn, no two of which are equal. In other words, an element in here is an injection from the set 1 through k, 1, 2, 3 up to k. It's an injection from that set into Rn. And this is the set of subsets of Rn with cardinality exactly k. And there's a map, which is a surjective map, that carries any injection from 1 through k into Rn to the image of that injection. We've seen this before, but I think for certain k's and different topological spaces here. And we endowed the codomain with the quotient topology through this surjective map. So before proving that this is a covering space, just reflect on what a preimage of an element here is. So an element in the codomain is a subset of Rn with exactly k elements. A preimage is, well, it's nothing other than a way of ordering those k elements. In other words, the preimage consists of all bijections between the set 1 through k and that set with k elements. So each preimage has k factorial elements in it. Now, because the domain is a subspace of a product, the k-fold product of Rn, and because Rn is Hausdorff, then any finite subset of the domain will be discrete, have the discrete topology. So already, that discussion so far is suggestive that this is a covering space. Now let's prove that it's a covering space. So, following the definition of a covering space, take an element in the codomain. So that's a subset of Rn with exactly k elements in it. And I just wrote what I said. The preimage by this map of the singleton consisting of just that subset alone is the set of all bijections or orderings of that set. Bijections of that from 1 through k to that set. That's a set. This set has k factorial elements in it. And we'll take that to be our discrete space F. F, I wrote that for fiber. So now we want to produce an open neighborhood around capital S and some other stuff. So what is that open neighborhood going to be? Well, the idea is, I hope you can see red. Suppose that's S and Rn is R2. So the idea is that we'll find a small enough epsilon so that an epsilon ball around those points looks like this. The epsilon balls around the points don't intersect. So what should epsilon be? We'll just let it be any number greater than 0 that's less than, say, half the distance between any distinct elements of capital S. You know that there is such an epsilon because capital S is finite, so these distances are bounded below. Now take capital U, the SOT subset, that consists of all the other cardinality K subsets of the plane that are just one element in each of these epsilon balls. So I wrote that out here. It's a set of all cardinality K subsets of Rn, such that, well, first off, as a subset of Rn, it's within the epsilon neighborhood of the set S. But second, it's that, so if I didn't put an and after that, the three x's here, those two and that one, would be a cardinality 3 subset of the plane contained in the epsilon neighborhood of capital S. Well, we want to disallow this. We don't want there to be two elements in capital T within the same epsilon ball. So that's what this and is about. One way of phrasing that condition over here is that this composite map be a bijection. And this composite map, call it alpha sub T, is the composite of first including T into the ball. You're assuming it's contained in that epsilon ball of capital S anyway. So it's first the inclusion, followed by the quotient onto the set of path components of that epsilon neighborhood. Now look, the set of path components is just this in natural bijection with S. There's a unique representative in each path component that belongs to capital S. So there's this quotient, and we just recognize that set of path components is S. So alpha T here is a map from capital T to capital S. We get such a map just by virtue of capital T belonging to this epsilon neighborhood of capital S, and because of how we chose epsilon. And the demand is that that composite map is a bijection. And you see that is the case for this situation, those three x's. When you collapse these balls to their center points, that set of center points being capital S, the map from the three x's to the centers is indeed a bijection, whereas for that situation, it was not a bijection. It was not one-to-one, nor was it surjective. So I'll leave it to you to check. This one's pretty easy. If once you have facility with the definitions, that this this subset U, this subset of unordered configurations, is in fact an open subset of unordered configurations. And again, to verify that amounts to thinking through the quotient topology on this set of unordered configurations. Now finally, we must produce a homeomorphism between U cross F and the preimage by that map of U compatible with their maps down to U. So I should say what phi is and argue that it's a homeomorphism. I'll do that by saying what phi is and saying what its inverse is, and then just noting that they're both continuous. So phi evaluates on an element of U, which is a T, and an element of capital F, which is a bijection from 1 to S. It produces, well, we're supposed to produce a new element in here, which is in fact Q of which belongs to capital U. And an element of here is an injection from 1 through K into Rn. So what is that injection? Well, sigma is a bijection between 1 through K and S. What we know, all we know about capital T is that there is this map alpha T associated to it that is a bijection. So we can post-compose sigma with the inverse of alpha T and then just include T into Rn. After all, it is a subset of Rn. The result is an injection from 1 through K to Rn. That's what phi is. or we'll take that to be what phi is. And what's the inverse? You can figure it out. So the inverse, it assigns to an injection, 1 through k into Rn. Call that injection little c for configuration. It assigns to that, well, you just look at the image of the configuration. It would have to be that on the u coordinate in order for this diagram to commute anyway, because that's how q is given. It assigns to an injection of 1 through k into Rn just its image. And then the f coordinate will be, well, do this, whoops. Yeah, right. What I had was right. Do C followed by alpha sub. It's just the notation that was off. Alpha sub t, where t is the image of C, and that will be a map from 1 through k into Rn, followed by alpha t, where t is the image of C, which is a bijection to S. The result is a bijection from 1 through k to S. And both of these are continuous. So that verifies that this also is a covering space.